Assignment problem. Assignment problem is problem of assigning n jobs to n machines. Assigning n jobs to n machines. This problem can be actually performed by using the assignment problem. So assignment problem is written as linear programming problem let n n jobs which are to be assigned to n operators so that the job is assigned to only one operator. Let there are n jobs which are assigned to n operators so that one job at least one job is assigned to only one operator. Constraint is only one job to one operator. So I is the index of the job and j is the index of operator. Job I equal to 1 to n. J is the index of operator. Cij unit cost for assigning job I to operator j. 'xij' equal to 1 0 if job I assigned to operator 0 is not assigned. The objective function of assignment problem is always minimization. The objective function of assignment problem is always minimization problem. So here also minimize the cost of assigning from of a job to a job operator. So minimize z equal to sigma I equal to 1 to n, sigma I equal to 1 to n Cij Xij. Since only one job is to operator, one operator, so we have to give the constraint subject to constraints sigma I equal to 1 to n Xij equal to 1 for all j equal to 1 to n. Similarly, for each operator there may be only one job assigned. For each job like one operator, for each operator also one job, vice versa. Non-negative constraint is Xij greater than or equal to 0 for all I and j. This is a linear programming problem. So here 2 points we need to note is assignment problem is always minimization problem. Assignment problem is always minimization problem. And another thing is it is always square matrix. Rows is number of rows equal to number of columns. So a n by n assignment problem can be written as, because a square matrix, right? N cos n is a number of rows, n is another number of columns. Assignment matrix n by n assignment matrix when tabulated as or when formulated as. So this when formulated as LPP, just now we have done that. When formulated as LPP, linear programming problem, then m square variables and 2n constraint equations will form. A n by n problem can be also formulated as transportation problem. When it is solved as transportation, the number of allocations n when it is solved as transportation problem, the number of optimal allocations are n minus 1 equal to 2n minus 1. The assignment problem, when it is solved as transfer function, it is always degenerate. Assignment problem is always degenerate, always degenerate when it is solved as transportation problem. Method used for assignment problem is Hungarian method. Before going to the method, we need to discuss about the steps how to solve the problem. So first is set of the square matrix. It is not square, convert it square. Set the square matrix. If it is not square, convert it to square matrix by adding dummy rows or columns. This can be written as first start. In flowchart I will explain. Write the problem in tabular form. Write the problem in tabular form. Is it a balanced problem? Check, is it a balanced problem? Is it a balanced problem? If yes, then go to the next step. If no, add dummy row or dummy column. And convert into balanced assignment problem, and check whether it is minimization problem or not. If no, if it is So check maximization problem, not minimization. Minimization means if it is, then you can go ahead. If it is maximization, then only you need to convert into minimization. So check whether the problem is maximization problem. If yes, then convert this into minimization problem. If no, then go to the next step. So convert it to minimization problem. How to convert to minimization is the subtracting by changing signs also you can convert, or by subtracting all of the values from the largest value is one method. So next, after doing that, check obtain the reduced cost tables. After obtaining reduced cost tables, subtract from all entries in each row the least value in each row. Subtract the least value in each row. Subtract the least value in each row from all the values in that row. It is called row transformation matrix. Then after this, do same thing with for column also. Subtract the least value in each column. Least value of each column from all the values in that column. After completion of this, check can all zeros be covered by less than n lines, less than or equal to n lines. Check can all zeros be covered with less than n lines. If yes, then improve the solution. Select the minimum of the solution. How to improve the solution is so you have to improve the solution. To improve, select the minimum of the uncovered cell values. Select the minimum of uncovered cell values. Subtract this value from all the uncovered cell values. Subtract this value from all uncovered cell values. Add this value to the cells lying on the intersection of any pairs of lines. Add this value to the cells lying on the intersection of any pairs of lines. Leave the cell values covered by only one line undistributed. So if here it is no, then make assignments on one-to-one match basis considering zeros in rows and columns. Make assignments on one-to-one match basis. Then stop. So this is a procedure for assignment problem. We do one assignment problem, then it will clear if you have any doubts. So if generally assignment problem is always minimization problem, if it is maximization, then we convert it into minimization by subtracting all elements from the maximum element. Consider an example of C1, C2, C3, C4, J1, J2, J3, J4. These jobs are assigned to these customers. 15, 29, 35, 20, 21, 27, 33, 17, 17, 25, 31, 37, 39, 15, 21. So first step is step 1. Check number of rows equal to number of columns. Balance the assignment problem. That is number of rows equal to number of columns. Step 2. Row transformation matrix. Subtract all values in that row from the sorry, subtract this lowest value from all values in that row. So after subtraction, for example, if you take the first row, C1 row, there 15 is the minimum, subtract 15 from other values. If you take second row, there 17 is minimum, subtract 17 from all other values. So similarly for others. After row transformation, the matrix will be 0, 4, 2 0 14 10 10 17 20 16 22 25 5007. Step 3. Column transformation. So in column transformation, subtract smaller value in the column from all the values. So first column smaller value 0, subtract 0 from all values, you will get the same values. In the second column smaller value is 10, subtract 10 from all the values. In the third column it is 16, subtract 16 from all the values. Fourth column smaller value is 0, subtract 0 from all the values. So after getting this, try to cancel the values with minimum number of lines. So now if you try to cancel, you need minimum 4 lines to cancel all rows. Minimum, suppose if I cancel this one, this one, this one. So I need actually I am using 3 rows to cancel the all zeros. So for this case, then I need to, because number of solutions are less than n, it has to be equal to the 4. So now if you cancel all this one, the values which are not cancelled, select the smaller value in that. Smaller value in that is 4. If you look at the table, I cancelled with lines, right? So after cancelling, you are able to cancel all the zeros with 3 lines, that is it is less than the n is equal to the number of rows or columns. So actually it is 4 rows in this 4 row square matrix, but the number of lines used for cancelling is 3. So it is less than, then it is degeneracy is there. So again you have to do the other method like subtract. Look at the non-cancelled values like 445 795 797. Out of this take minimum value and subtract it from all other non-cancelled values and add that 4 at the cross section of the points, like 4 comma 2 for 4 comma 2 0. After adding 4 to 4 8, again after adding 4 to 2 6 0. Here remove the 4, remove 4, subtract minus 4 from 5. This will be same, this will be same cancelled values. Here subtract with 4, subtract with 4, subtract with 4. Now you got a matrix which can be cancelled with only minimum 4 lines. So minimum 4 lines are used to required to cancel. So then you take this matrix and try to assign that one. So this is the final matrix, because number of rows are equal to the number of lines used for cancelling the zeros, right? So 0 8 6 0 0 0 0 3 0 0 6 5 1 0 0 3. So now you start cancelling the zeros. If you cancel the 0, cancel this, try to select a row column with less number of zeros. So first I selected this, cancel. So this corner point is called assigned value, and select another row column, cancel this. So this value is assigned and this value is assigned, corner point, cross section point. Select this value and this value, cancel this value is assigned, cancel this and this value is assigned. So how C1 to J2 is assigned as, so value is 29, C2 to J3 cost, assigning cost is 33, C3 machine is customer is assigned to J4 job 15, customer 4 is assigned to J1 job 14. After summing it is 91 is the cost. If number of zeros are more than the matrix, then multiple solutions are possible. Here number of zeros are more, so then it's why multiple solutions may be possible. That's about simple transportation problem. We do another one problem which they have asked in GATE previous questions. So question number 16. Question number 16 in page number 106. Question number 16, page number 106, GATE 2006 question. A firm is required to procure 3 items PQR. The pieces quoted for these items by suppliers S1, S2, S3 are given table. The management policy requires that each item has to be supplied by only one supplier and one supplier supply only one item. The minimum total cost for procurement to the firm is. So he has mentioned one supplier to one procurement. The management policy, each item has to supplied by only one supplier. One supplier has to supply only one item. Okay, supplier to item relation, assignment. It is assignment problem and it is minimization problem given already. So first take the first table, PQR. S1, S2, S3 are suppliers. Cost of supplying is 115, 125, 120, 140, 145, 130, 140, 165. Check matrix is balanced or not. So it is already square matrix, it is balanced. Matrix is balanced rows equal to columns. It is minimization problem, so it is also checked. Then first calculate row transformation matrix. Row transformation matrix is calculated by select minimum value in each row and subtract it from all other values in that row. For example, take first row, minimum value is 110, subtract that minimum value from 120 and 130. So 110, 110, 110 minus 110 0 and 120 minus 110 is 10, 130 minus 110 is 20. Similarly remaining rows also 0, 25, 25, 0, 20, 40. This is the first step. Second step, step 3, column transformation matrix. Create column transformation matrix. So for column transformation matrix, again similarly subtract the values, minimum value from the other values in that column. 10 is minimum value in column 2. Subtract this from other values. So subtract here 20 means 0, 5, 20. Check whether you can cancel all the zeros with less number of lines. So now you can cancel all the zeros with 2 lines. So there is a degeneracy. Again improve the solution. To improve the solution, check the values of non-cancelled numbers. 5 is the minimum value. Subtract that from other non-cancelled numbers. So and add that value at intersection 5, 0, 0, 0, 0, 10, 5, 0, 15. Now again cancel the zeros. It takes minimum 3 lines to cancel. So now the problem is balanced. Now find the optimal allocation. So for optimal allocation, select the minimum any row or column where minimum zeros are available. So minimum zeros are available in last row. So select that and cancel that one. So this is one allocation, and another allocation is this is one allocation, and this one is another allocation. So look the values corresponding to that. So P to S2, Q to S3, R to S1 values are P to S2 is 120, here it is 140, here it is 125. Answer is 385. That's it. So this assignment problem is also can be used to solve the traveling salesman problem. We do one traveling salesman problem, how to allocate traveling salesman problem. Before that, what is traveling salesman problem? So traveling salesman problem is to allocate minimum route such that he can travel all cities at once and come back to the starting city. So traveling salesman problem starts at one city and visits other cities and comes back to the starting city. Salesman starts at one city and visits other cities and come back to the same city, such that the only once you have to visit the city. This is called traveling salesman problem. Solution procedure to the traveling salesman problem is similar to that of assignment problem, but only difference is allocations. Here when we are allocating well 0 in a matrix, same time we may get repeat city in the matrix. So we need to careful While allocating one city, you have to, you have to allocate only once for each city. So if we do one problem on this traveling salesman problem. So a traveling salesman started with city 1. So 1 to 1 he don't have to visit because already it's one place. That's why we have to assign with infinite value and bigger value. 1 2 3 4 5. 1 2 3 4 5. Infinite 1 1. For fourth it is 2 5. Second one, it is infinite or null, so like an undefined number 3 5 3. When we need to assign that undefined is when we don't want to allocate. 8 undefined value 6 7. The cost for the traveling from one city to another city. 2 2 5 infinity 6 4 3 1 5 infinity. So start with row transformation. Step 1, it is a row matrix anyway, square matrix, it's checked. Row transformation. And column transformations also we do one step only. So first row transformation. Subtract lower value from all the values. It is infinite or undefined. Just undefined, give undefined value. 0 7 1 3. 0 undefined value 7 1 2. 0 2 undefined 4 0. 0 3 4 undefined 3. 2 0 4 3 undefined. That is row transformation. Similarly, column transformation. 1 2 3 4 5. 1 2 3 4 5. So this is undefined value. This is 0 3 0 1. 0 undefined 3 0 0. By subtracting that value 0 2 undefined 3 0. Subtract that 0 only. It's column transformation. Sorry. So next after this, check whether the routes are, consider this as a source, this as a destination. So if you start at one point, you have to come back from that point to the same point. So 1 2. If we start at 1, so 1 to 2. So 1 to 2 I have gone. So from 2 to there are options like 4 or 5. 0 is available at 4 and 5. So if we take 4 and again 4 to 3 is there. So look at the 3 value 3 to 5. This is one assignment. So here you can't you are not coming back to the initial starting city. So that's why it is allocation is wrong. So again start allocating with some other method. like 1 start at 1, 1 to 4, because for there is option like 1 to 2 and 1 to 4 are chances are there. Wherever there is 0 you can go to there. So here in first row there is 0 at below 2 and 4, so you can go to 4 or you can go to 2. We have tried with 2, now we will try with 4. 4 to you have option only 3, from 3 to you have option only 5, from 5 to you have option of only 2 and 3. So already 3 we went, so we can go to 2. 2 to again 4 and 5 are already gone, so 1. So this is a best allocation assignment, traveling salesman problem. So this assignment problem is always mean one point we need remember is few points like this is always a minimization problem. If it is given as maximization, convert it to minimization by subtracting all values from the bigger value. Next method is it has to be always square matrix where rows is equal to the columns. If it is not square matrix, convert it to square matrix by adding either rows or columns. Then you have to go through row transformation and column transformation. Then check the number, cancel all zeros as minimum as straight lines. If the number of straight lines cancelled for zeros is less than the number of rows or columns of that assignment matrix, then you have to improve the solution. Otherwise, that is the best solution. Allocate whatever allocations you will get is the best allocations. That is about transportation problem.